Madam? Good afternoon, participants.
Hello.
Madam. Yeah.
Yes, yes.
How are you, madam?
I'm fine, fine. How are you?
Fine, madam. Fine, madam.
Yeah. Participants are joining, still joining. Yes, I am seeing.
Yes, madam. But let us start, madam. No problem. They'll join, madam. I think.
Shall we start?
Yes, madam. We'll start, madam. Madam, yeah. I request my colleague, madam, HOD, cleaning department, Mr. Sarun Kumar, to introduce to madam. Madam, actually, Mr. Sarun Kumar is from, he did his MTech from. Civil department, we have 10 madam.
Okay, okay. And now of that, 4 from IIT Kharagpur. That's good.
Madam, actually, we have fortunately, the faculty members, if you can see, most of the faculty members are from either IIT, NIT, or Central Universities, madam.
Very good, very good. Yeah.
At least 1 degree from any of these universities.
Okay, that's good. That's good.
Okay, madam. We welcome you, madam, once again, and thank you, madam, for accepting our invitation. So now I request HOD, Mr. Sarun Kumar, to introduce.
Thank you very much, sir. Good afternoon, all. Let me introduce Dr. Swati Maitra. He is an assistant professor in Kanvi and School of Infrastructure Design and Management in IIT. She applied her PhD.
Sound is not very clear.
Yes.
For you also, I think it is so.
Yes, madam. Yes, madam. Some problem.
Just a minute.
Okay, no problem.
Sir, ನಿನ್ನ ಬರ್ತೀನಿ ಸರ್. Yeah. Am I audible, ma'am? No?
Yes. Now it is better. Better.
Good afternoon, everyone. Let me introduce Dr. Swati Maitra. Is an assistant professor in Ranbir and Chitragupta School of Infrastructure Design and Management, IIT Kharagpur. She obtained her PhD in civil engineering from IIT Kharagpur and masters from IIT Bombay. She worked in industry for about 8 years. Her research areas include concrete pavement analysis, design, performance evaluation, concrete overlays or white topping, sustainable concrete and cementitious materials, retrofitting, and rehabilitation of civil infrastructure. Dr. Maitra has several research publications in book chapters, international and national journals and conferences. She has received several awards like that fellowship by the German Academic Exchange Services, Bihar PWD medal by the Indian Roads Congress, and others. Dr. Maitra is actively involved in a number of research and industrial projects. With that, I request Dr. Maitra to carry forward the session. Thank you very much.
Thank you. Thank you, everybody. First of all, shall I start, Dr. Amarendra?
Yes, madam.
Okay. First of all, I would like to thank the organizers, Dr. Amarendra and others, other faculty members who are here for inviting me for this faculty development program of this institute. And I am really thankful to them, and it's my pleasure also to interact with them and other participants. So from my behalf, I welcome all the participants for this session. And you have come from different institutes, different backgrounds, and so after the lecture, just feel free to discuss also. So I will now start my presentation. Just a moment. Is the screen visible? Is the screen visible?
No.
Is it visible? Is the screen visible?
No, ma'am.
No.
Yes. So, what is?
Madam, just open your presentation. Just go to the present now.
Present now I'm going, right? Then your entire screen, it says.
Yes, ma'am. Share your screen, ma'am.
Okay. Yeah, now is it visible? No, not yet.
No, madam.
Why? Share. Okay. What happens? Present now, I am just doing it. Your entire screen, okay? Then what happens?
Madam, no, present now.
Present now I am doing.
And entire screen, madam.
And share your entire screen. That thing comes.
Yes,
but where?
Then your presentation. Click on your presentation, madam.
I've clicked on my presentation. This is PDF file. Is it visible?
Oh, it's a PDF file, madam.
Or shall I open the PPT?
A PPT, you open PPT, madam. That will be better.
That will be better? Okay.
Yes,
okay. Just a moment.
press present now, madam.
I'm opening my PPT.
Just
Normally
open.
it is of now.
Now come to screen and just press the right side, madam. Bottom button is present now.
But why it is not showing it here? Present now. Again, it is not coming. Why? I don't know. I have done it for so many times. But
Madam, when you press this present now, are you getting this? Your entire screen
still not visible.
No, madam.
Just a
No,
moment.
madam.
Madam, otherwise, can you just leave and join again, madam?
Okay.
Some problem is that just
Maybe.
leave it and join again.
So I will open my presentation, right, and then I'm. It's not showing. I don't. Just one more. Just a moment. Just a moment. Present now.
Your entire screen.
এখানে চলে আসছে।
Select.
কোনটা?
Okay, share.
এইবার এসছে।
Share. Now off it. छोटा करो.
Is it coming?
Yes, madam.
Coming?
Yes, madam.
Go to the presentation.
Okay, slide show more.
Go to slides.
Okay, so it is visible now?
Yes, madam. Fine.
Okay, fine.
Right now.
Okay. Okay. Sorry for the delay. So today's topic is characteristics and design of rigid pavement, though I will mainly focus on the characteristics of rigid pavement. And this is just an introduction. Road infrastructure, the main component of any road infrastructure is the pavement, and we have bituminous roads and concrete roads, and I think this is only this FDP is only on concrete roads, so I'm not going into detail. We have you can compare it: construction cost, maintenance cost, durability, and life cycle cost. So in recent years there is a significant emphasis from the government for the construction of concrete roads in India. The concrete roads, we have several types of concrete road: jointed plain concrete pavement, or JPCP in commonly we call, jointed reinforced concrete pavement. Though this is not very common, even not in India, and even in abroad also, this is becoming less nowadays. And in jointed plain concrete pavement, there is normally no reinforcement, and we will discuss those things. In jointed reinforced concrete pavement, it has reinforcement. Continuously reinforced concrete pavement is another type of concrete pavement where we have continuous a good amount of reinforcement throughout the concrete slab. Pre-stress and precast is another type of concrete pavement where you can build the concrete slab in a factory and can place it on the site. And it could be pre-stressed so that it can take more load, and the thickness requirement is also less. Roller compacted concrete pavement is also another type of concrete pavement. Self-fill concrete pavement is normally for low volume roads, village roads, like that. Pervious concrete pavement is also another type of pavement, new type of pavement, comparatively new. And concrete is generally impervious in nature, but this type of pavement is, from the name you can understand that this can permit water. So for low volume roads or for urban areas, this type of concrete pavement can be used. And another is the concrete overlay or white topping. This is also coming in a big way nowadays, and this is mainly a rehabilitation measure for the existing bituminous roads. So there could be several types of concrete pavement, but the most common type is the jointed plain concrete pavement. And in most of our highways, we have this jointed plain concrete pavement. And our main focus of today's presentation is on jointed plain concrete pavement. Now let us talk about the characteristics of concrete pavement. Concrete pavement is composed of mainly the concrete slab, and this concrete slab has high flexural strength. So concrete is generally a material which can take up very high compressive strength, and of course its tensile strength and flexural strengths are comparatively low, but the strength of the concrete slab that governs the concrete pavement design mainly. So it has concrete slab at the top surface, and below it is the foundation. So the foundation is actually composed of the base layers, sub-base layers, and the compacted subgrade. And in concrete pavement, the influence of subgrade is comparatively less as compared to a bituminous pavement. In case of a bituminous pavement, it is actually the layered structure, and all the layers are responsible for taking up the load. So the thickness also decreases as we go downwards. In case of concrete pavement, also we have different layers. Is that any problem, Dr. Amarendra?
No, madam. Please
continue.
Okay.
Okay. You can tell the participants to mute so that there will.
Madam, but one or two.
Yeah. Okay. It's okay. No problem. I continue. So in case of concrete pavement, also we have different layers. Like as I said, concrete slab is the top surface. At the top surface, then we have base layer, sub-base layer, and the foundation. But it is the responsibility of the concrete slab itself to take up the load. And base and sub-base are there to support actually the concrete slab. So this constitutes actually the foundation for the concrete pavement. And so the foundation can be said that it is composed of subgrade, sub-base, and base layers. Here in India, we have sub-base layer, maybe granular layer or a cement-treated layer, or WMM, which is now commonly used, constructed. And in base, as a base, we have generally dry lean concrete. So that dry lean concrete is of concrete of lower strength. The strength is about M10 or 10 Newton per millimeter square at 7 day. So not very high strength as compared to the concrete slab. Concrete slab we have generally of M40 grade, that means 40 Newton per millimeter square at 28 days. So it is the high strength of the concrete slab that is taking up the load, and less influence of the subgrade strength. Rather, where the subgrade strength is low, we prefer that the concrete pavement to be constructed. And since the high rigidity of the slab, concrete slab, it has smaller deflection as compared to the bituminous pavement. And also we have, particularly in this jointed plain concrete pavement, we have joints. The joints are very important component in concrete pavement, and I will discuss those in detail. So we have finite slab as contrary to the bituminous pavement. Bituminous pavement, you will find continuously it is being constructed, whereas in case of concrete pavement, we have joints in transverse as well as longitudinal direction. And another important component of concrete pavement is the interface between the concrete slab and the foundation. So the foundation means that is the base, subbase, and the subgrade. So the interface of concrete slab and in between concrete slab and the base may be bonded interface or unbonded interface. So both interfaces have their own benefit and limitations, so that we will discuss later. But this interface has a significant influence on concrete pavement performance. So the main components, as it is said, are the concrete slab, the foundation, the interface, and the joints. And since the rigidity of the slab is high in case of concrete pavement, so the load dispersion is also at a wider area. And this load finally goes from concrete slab to base, subbase, and to the subgrade, but on a wider area. So the stress which is coming on the subgrade is also much less. So that is why it is when the subgrade strength is low, it may be a better option for a concrete pavement construction. This is just a schematic diagram of the concrete pavement. You can see this is the first picture is the top view, and these are the lines. You can see that these lines are the joints. So the joints are along the transverse direction and along the longitudinal direction. So along this is the arrows are for the traffic movement. So along the traffic movement, you will find that these are the joints, and these are transverse joints, and transverse joints are provided with dowel bars. And this is the longitudinal joint, and longitudinal joints are provided with tie bars. We will discuss these things. And this is the just a sectional view of the pavement. Sorry, concrete slab, the dry lin concrete base, the sub base, and the subgrade. Now, the structural behavior of concrete pavement, it depends on the traffic characteristics. It also depends on the climatic characteristics. The main load which is coming on the pavement is due to the traffic movement. The traffic is the main loading on the pavement. For all types of pavement, it is the main load. So the traffic characteristics is an important consideration for the performance of the or the design of the pavement. So traffic characteristics means not only the load, the tire pressure, the wheel position, the wheel distribution, whether it is single axle, tandem axle, or tandem axle, and what is the tire pressure, or what is the total load coming on the pavement. So all that matters and in developing the stresses. So the traffic load or the axle load is the main load coming on the pavement. Another important is the temperature variation. Climatic characteristics mainly is due to the temperature variation and the moisture variation. The temperature variation could be daily variation and seasonal variation. Both each has its own effect on the development of stress on the pavement. And moisture variation is also there. And of course, the effect of moisture is much less as compared to temperature variation. So often in the analysis or in the design, we neglect the effect of moisture, but it has a similar type of effect as temperature. Soil characteristics also influence the performance of the pavement, because it is the soil or finally it is the subgrade or it is the foundation of the pavement. So for all structures, the foundation matters. So that is why the soil characteristics also in a similar way influence the structural behavior of the pavement. And material characteristics, like similarly for any infrastructure, which is whether it is made up of concrete or bitumen or steel or whatever it is, the material is an important consideration. So material characteristics also important for the structural behavior of the pavement. And the critical stress is actually due to the effect of combined effect of wheel load and temperature. So those things we will discuss subsequently. Now, jointed plain concrete pavement, as I said, concrete slab is the main component, main structural component. It is the plain cement concrete without having any reinforcement, and it is responsible for the load carrying of the pavement. Foundation, it is a combination of subgrade, base, and subbase, as I said, and the foundation actually is assumed as Winkler foundation. Here, for all our analysis and calculations, Winkler foundation model has been assumed, which is a very simplistic model, as suggested by Westergaard, who is considered as the father of concrete pavement analysis. And from that, we still use Winkler foundation. Of course, in some analysis, elastic foundation also can be used, but still Winkler foundation model is quite popular. And in Winkler foundation, the subgrade strength is expressed by one single parameter that is called modulus of subgrade reaction. And this parameter can be found out from plate load test, or it can be correlated from CBR value. And base and subbase, as I said, it is for uniform and firm support for the concrete slab. Now the interface, as I said, it could be bonded interface or unbonded interface. Bonded interface, that means when the concrete slab at the top is cast directly over the base or subbase, then we call it a bonded interface. And so the interface between these two is very rough, and the friction between the two is very high, because that is the lower layer is also, in most of the cases, it is dry lean concrete, and even if it is a say WMM also, in that case also it is quite high, the friction, if the concrete slab is cast directly over the base. And in case of unbonded interface, there is a bond breaker in between the concrete slab and the dry lean concrete base. So that bond breaker could be an asphalt layer, a very thin asphalt layer, or a polythene sheet, or some type of, or any other type of polymer material. And generally in India, we use polythene sheet, very fine 125 micron polythene sheet as a bond breaker. And so this interface can also be called as a smooth interface. Bonded interface can be termed as a rough interface, whereas the unbonded interface can be termed as a smooth interface because it has very low friction. Joints are integral part, as I said, and in the morning also sir has discussed that the joints, and different types of joints and why they are provided. Also we will discuss a little bit here. So we have here in JPCP 4 types of joints: contraction, construction, expansion, and isolation joints. So these joints are provided to control cracking due to shrinkage or thermal contraction, moisture, or thermal variation within the slab. And as I said, that the joints are provided in transverse as well as in the longitudinal direction of the pavement. So normally, as we know, that concrete is a material when the main ingredients are cement, aggregate, sand, and water. And so when water is added actually in the dry mix, the hydration of the cement takes place. So this hydration, this cement hydration is an exothermic reaction. So a lot of heat is developed, a lot of heat is generated. So if we cannot control this, so then there will be loss of water. So water will evaporate, and because of that, hydration cannot take place. If we control this evaporation of water, then hydration can take place in a proper way, or sometimes we put additional water so that it gets sufficient water to hydrate. So that is why curing is necessary in all concrete structures. But if it is very, very difficult for many structures to control this type of cracking, otherwise this shrinkage cracks may occur, and it may occur at random location, at anywhere. So it is very, very important to control this type of cracking. So proper curing is very much necessary for all concrete structures. And particularly for mass structures like this, pavement is a mass structure, is a huge structure, and a lot of the entire surface is actually open to atmosphere. So with larger surface area, more water can evaporate. So it is very important for the concrete pavement construction, the quality control, and so that the water cannot evaporate and proper curing can take place. So that is why it is very important. Otherwise, if we cannot do it properly, then cracks may occur anywhere. It may occur at random locations. So what we do here, we know that sometimes it will be very, very difficult to control or manage cracks. So that is why what we do, we create some weak points intentionally beforehand, so that we know the location of that weak points, and if crack occurs, then at the weakest point it will occur. So what we do, we cut grooves, and since we know that we are creating weak points on the slab, so that is why to take care of that weak portion, we put some extra measure, so that that portion, even if it cracks further, it will not remain a weak point. So what we do, we cut the slab at a desired location at regular intervals and provide dowel bars. So we know that if crack occurs, then it will occur at the weakest locations, and those are the saw cut locations, are the weakest locations. We created it, and because of that, we are providing dowel bars. Yeah. So we have contraction joints, contraction joints to allow cracks due to thermal contraction. We also have construction joints to separate successive construction activities. These construction joints, suppose we are constructing the pavement, and after some time we have to stop the work. Say a day's work is over, so we have to stop it. So there we need to provide a full depth construction joint. So that is necessary, and we have to provide dowel bars there. So construction joints are provided to separate the successive construction activities, and expansion joints are provided to permit the thermal expansion of the slab without damaging the adjacent slabs or structure. Expansion joints are not provided in India in concrete pavement, but they are provided at the near the structures. So that needs to be provided. Or isolation joints or expansion joints are provided only at the adjacent to the structures. But contraction joints and contraction joint and construction joints have to be provided. And other these expansion or isolation joints need to be provided when there is an adjacent structure. So for that, you have to provide these two types of joints. So here, I think similar pictures sir has also shown in the morning, but this is just schematic diagram. So I'm again showing quickly. So this is what we do here. This is the undoweled slab. We are saw cutting it at 1/3 of its depth, 1/3 to 1/4 of its depth, so that the crack occurs below that saw cut. And since those are the weakest locations, so we provide dowel bars at that location. So that is the contraction joint in pavement. In case of longitudinal joint, similar thing. Here also we cut it along the length of the pavement, and same 1/3 to 1/4 of the slab depth, and we provide tie bars. Of course, tie bars are the diameter of the tie bars are much less as compared to dowel bars, because the function of the two bars are different. Dowel bars are provided to transfer the load from one slab to the other slab. However, the function of the tie bar is not that. Tie bars are provided to hold the two slabs in their positions. They are not for load transferring, but just to hold the slabs in their positions. Tie bars are provided. So here you can see that the schematic diagram of the tie bar at the longitudinal joint of the pavement. Here, after the pavement is constructed, the grooves are cut, and this has to be cut within 18 to 24 hours of the pavement. Otherwise, again, shrinkage cracks may occur. So this is also a very, very important thing, that we have to cut the grooves with proper depth and also within a stipulated time, that means within 24 hours. Many of the cases it has been found that because of the late thaw cutting, cracks have occurred on the pavement, and there are other distresses followed by. And it has been seen that we have seen also in NH 60 that after the groove cutting, when we open that side of the pavement, or we have removed the shoulder portion, cracks have been found below the socket. So this is good. Otherwise, it may occur at any other location. So we want that cracks to occur and only at the socket locations. So this is the contraction joint created below the socket of the pavement. This is construction joint. Construction joint is full depth joint, because we have to stop the day's work or night's work, whatever it is. So when we stop our activity, so we need a full depth construction joint, and that is why we have to provide dowel bars, because load has to be transferred from one panel to another. So those things, load transfer we will discuss in detail. But here it is just the construction joint, and you can see that it is a full depth joint. So no additional crack will form here, but we have to provide dowel bars for the load transfer. For longitudinal case, we need to provide tie bars as well in the construction joint. Longitudinal construction joint, tie bars will be provided to hold the slabs in their position. Now, this is just a picture of dowel bars and tie bars in a construction joint. You can see here, this is a construction joint, and these are full depth construction joints, and dowel bars are there. You can see the diameter of dowel bars are also larger as compared to tie bars. Generally, dowel bars are of the range of 32 to 36 millimeter diameter, and the diameter of tie bar is 12 millimeter, 16 millimeter, like that. So a lot of difference in their diameter based on their the purpose. Dowel bars are for load transfer, while tie bars are just to hold the slabs. This is expansion or isolation joint. This is also full depth, has to be, and with wider gap in between. And you can see that sometimes the edge also is being thickened, so that to avoid damage also at the edges. So this is expansion joint and isolation joint, the JPCP. Now, as I said, that load transfer is a very important component in jointed plain concrete pavement, because it is not a continuous structure. So the slabs are formed because of these joints at the transverse and longitudinal directions. So load has to transfer from one slab to the other. So, and how the load is transferred, or how better the load is transferred, that actually governs the performance of the pavement. So it is very, very important that load which is applied on the slab is shared by the adjacent slab, and this gives the performance of the pavement. If there is, if the load transfer is poor, then a lot of distresses may happen. Faulting type of distress or pumping, erosion, corner breaks. I will show you some pictures that there will be several distresses occur if the joint is not properly constructed or not properly sealed or not, or the load transfer is not proper. Okay, so there could be many reasons for distresses. So those things I'm not covering, but I will show some pictures that how the joint-related distresses occur in JPCP. And the performance of the pavement actually is expressed by a factor or a parameter called load transfer efficiency. The load transfer efficiency is that the ability of the pavement slab to transfer the load from one joint to its adjacent joint. And so this load transfer is done by mainly two mechanisms. One is the double bar system, another is by the aggregate interlocking system. And in some cases, it is the combination of the two. Now, load transfer, it is very important to transfer the applied load from one panel to the other panel. And this load transfer is expressed in percentage and can be measured by measuring the deflection of the loaded slab and the deflection of the unloaded slab. So it is actually the load transfer efficiency is actually the ratio of the deflection of the unloaded slab to the deflection of the loaded slab, and is expressed in percentage. So you can, from this expression also, you can understand that if the unloaded slab deflects equally with the loaded slab, then the load transfer efficiency is 100%, which is the ideal case. But it is ideal case, theoretical case, it cannot happen. So it is when the unloaded slab deflects very near to the loaded slab, then the load transfer efficiency becomes high. So it is the purpose of the designer or the construction people that the load transfer efficiency should be very high. So because that governs the performance of the pavement. So now you can see here that distresses due to poor load transfer at joints. Here it is faulting at longitudinal joint. This picture you can see here that a lot of gap has been formed. This has happened in NH60, unfortunately, and we have seen it here. And then this was repaired, retrofitted, strengthened, and this thing you cannot see it now because it was completely replaced. And this happened, of course, due to improper settlement of foundation, possibly, and maybe some other distresses. So there will be a lot of gaps and difference in levels also in the two portions of this. And this is faulting and blow up of transverse joint. This happens because sometimes the gap between the two adjacent slabs are not sufficient. So when due to thermal expansion, the slab tends to expand, and if there is no sufficient gap, so then it will try to go up to take its space. So because of that, there will be a collision of the two adjacent slabs, and this type of distress may occur. So this is called blow up type of distress. And if that type of distress occurs, then you cannot do anything. You need to replace the slab panels. So this is blow up type of distress and all joint related distresses. This is falling from bad construction joint. You can see that material will come out from the joints. It is not properly sealed or it is damaged. So this type of things may happen. Pop out near the joints. You can see here that maybe because of high stress developed at the corners, the portions are damaged. Spalling also occurs. So these are all joint related distresses in JPCP, very common. You can see here these are all joint related distresses. Fines were pumped out You can see here there will the water and other materials may come out from the bottom to the top, and you can see here the picture A, and in picture B you can see here that because of maybe foundation improper settlement or some other reason, or improper tie bar connection, there are settlements. The two slabs, there is a difference in level. You can see here. So these are all joint related distresses that occur in jointed plain concrete pavement if the joints are not properly constructed and treated and maintained. So joints, particularly in JPCP, joints need to be sealed also, so that the water and other materials and dust particles should not go inside and damage the underlying layers. And if that thing happens, then it may damage the subgrade, may cause erosion, it may cause voids below the slab, or it may damage the base and sub-base layers. So it is very important to maintain the joints, and often joints are found to be the main distress areas in case of joint JPCP if it is not properly constructed or maintained. So proper sealant also need to be provided just after construction, both in the both in the transverse joint as well as in the longitudinal joint. So proper sealants need to be provided in JPCP joints. Now we will discuss the load transfer mechanism. Load transfer across transverse joints, I have told that it is due to double bar system and aggregate interlocking system, and or it could be a combination of the two. Now, in case of double bar system, double bars are actually mild steel bars which are provided mainly for the load transfer. Load transfer from one panel to the adjacent panel. So it connects the two panels at their mid depth of the slab, and double bars have to be provided when we have a pavement which is subjected to high traffic volume, and comparatively the joint spacing is longer. Okay, and so for all those cases, double bar has to be provided in the joint. So double bars allow the adjacent slab to expand or contraction also, because in those joints you have the joints are provided. So double bars, one side of the double bar is actually provided with some grease or with plastic cover, so that it can take care of the expansion. So it allows the adjacent slab to expand or contract also, and it provides the good riding quality by preventing the fault. If double bars are not provided, then one slab which is loaded, that only will deflect, the other one will not. So as a user, will experience a jar from the movement. So it allows the double bars, when they are functioning properly, they enables a good riding quality also to the users. So this picture also shown by sir, but still I am using it. You can see here from this picture that it is no load transfer when there is no measure has been taken. That means no double bar is there. So the slab which is only which is subjected to load will only deflect. The other one will not. So as a road user, when the vehicle moves, it will experience a jar, and that is not comfortable for the road users. Also, it will damage the loaded slab at the edge. So so this type of thing we want to avoid. So for that, double bars are provided, and you can see that when double bars are provided, both the slabs bend. Of course, the ideal condition is both the slabs bend equally, but this is theoretically only. But as close as possible, when the double bars are functioning very good, properly, then both slabs deflect almost equally. So it is a smooth variation from the loaded slab to the unloaded slab. So double bars actually also bends the unloaded slab. So this helps in transferring the load. So that means the loaded slab also deflects, the unloaded slab also deflects, and the load is transferred from the loaded slab to the unloaded slab. So this is the function of dowel bar. So, it provides the load transfer from the one panel to its adjacent panel. Now, on what factors these performance of the dowel joint depend? So the dowel joint parameters, it depends on these factors. That means the diameter of dowel, the embedded length of dowel. Here, some portion of the dowel, the half portion is on the left-sided slab, another half on the right-sided slab. So the total embedded length matters actually, that how much the performance of the dowel. The spacing of dowel, because the dowel is actually taking up the load. So it is the dowels which are placed at a regular interval across the transverse joint. So spacing of the dowel, diameter of the dowel, embedded length of the dowel are important parameters for the load transfer. Another parameter is modulus of dowel support. I will tell little late. Next slide, I think. Next slide, yes. Modulus of dowel support and dowel looseness also I will discuss in detail. Those are important parameters. Joint opening also in case of dowel joint opening matters. May not be very significant, but still that matters. And of course, the properties of the material, that is properties of steel. The dowel bars are made of steel. Properties of concrete, which is the slab, and the strength of subgrade. So all these parameters actually influence the load transfer from one panel to the other panel. So when we will go for design so all these things actually are responsible. Okay. Or for analysis, we will see that actually the load transfer efficiency depends on all these parameters. Now, what is modulus of dowel support? Modulus of dowel support, it is an interaction between dowel and concrete. It's a hypothetical term, but it represents the interaction between dowel and the concrete. So the dowel bars are embedded into the concrete. So the interaction between the two is very important. So that is represented by this parameter, modulus of dowel support. So a high modulus value indicates a very good contact between the surrounding concrete and steel. So when the modulus value increases, load transfer efficiency also increases. So for our analysis purpose, we have the K value ranging from 80 to 600. So that can be determined also from experiment. So that is the thing. So this is called modulus of dowel support. And relative stiffness of dowel embedded into concrete is also another parameter which is expressed by a term beta. So beta is a parameter which is called relative stiffness of dowel. And all these parameters are there to represent the load transfer due to dowel bar system. So beta is a parameter which depends on this modulus of dowel support. D is the diameter of the dowel, and E and I are I is the moment of inertia of the dowel bar, and E is the elastic modulus of the dowel bar. So this is a relative stiffness of the dowel. So that is a parameter. So modulus of dowel support is actually represents the interaction between the dowel and the concrete. So that influences the load transfer efficiency by dowel bar system. Now, dowel looseness is also another important consideration. Dowel looseness, actually, the dowel bars are embedded within the pavement. So the contact between the surrounding concrete and the steel may deteriorate over time, because you see that the dowel at the edges, at the joints, dowels are provided, and up to it is not very long. The dowel bars are normally 600 mm or so. So half is embedded here and half is embedded in the adjacent slab. So, and with repeated application of the load, particularly at the joints, what happens? The interaction between the dowel and the concrete actually deteriorated. And because of that, there may occur some looseness at the dowel and concrete. So dowel is at the initial, just after construction, it is just embedded tightly within the concrete. But with over a period of time, over several years, due to repeated application of load, so what happens? Some gap actually exists in between the dowel and the concrete. So that is called actually dowel looseness. And if that thing occurs, actually the dowel will not perform adequately. That means the load transfer will not be high. That means the loaded slab will deflect more as compared to the unloaded slab, or the unloaded slab will deflect less as compared to the loaded slab, because the dowel functioning is hampered due to this looseness. So this is actually the voids which are developed around the dowel, okay, due to repeated application of load, and it may occur at all joints, all dowels, or it may be more at the wheel path. So it may happen. The looseness may vary also along dowel length, and actually because of this looseness, the efficiency of the dowel may reduce. Okay, so we have done some modeling. Also, actually, during my PhD work, I have done modeling, a lot of modeling on concrete pavement, and all these main components of the concrete pavement was modeled, like the interface, the dowel joint, and the aggregate interlock joint, and all those things have been modeled. And I will just very quickly show also those things. So this is a finite element model. You can see here, these are the red one is the concrete slab, the violet is the shoulder portion, and in between there are tie bars, and below the concrete slab is the DLC, 150 mm DLC, and below that it is 150 mm WMM, and the below is the subgrade, which is represented by Winkler foundation. And Winkler foundation is nothing but a spring foundation, so it is represented by these straight lines. Actually, this construction is this geometry is the NH60 thing. So I have modeled that pavement actually, and the longitudinal joint also you can see, and this is the transverse joint. Here you can see the transverse joint has also been modeled, and dowel bars were also modeled. So this is the complete model. Only two panels are shown here, and with all the layers, with transverse joint and longitudinal joint. And then I have analyzed and found out the stresses, load transfer, all those things. So in the finite element modeling, the main components, as I said, the main components of the JPCP, which are the concrete slab, the foundation, and foundation is composed of the base and granular subbase, and the subgrade is the Winkler foundation. So subgrade was modeled as Winkler foundation, and base and subbase was modeled as elastic material, and they were modeled using solid brick elements, and concrete slab was also modeled as a solid brick element with linear elastic properties, isotropic properties. And now here, this is the finite element representation of the dowel bar, and you can see here that this is a cross section of the dowel bar system shown as a schematic diagram. One side is loaded, the other side is the unloaded slab, and the dowel bar is provided embedded in both the slabs, and in one side there is gaps around the dowel. So that gap may vary. It may be 0 or it may not be 0, but it may be of some few millimeters, but that matters a lot. So this is around gaps around the dowel. So that is actually the dowel looseness. And this is the below picture is the finite element representation of that. And this was a 3D model, as you have seen in the last slide. So this is a 3D model, but this shows the 2D view. And here, this is the brick elements, and for slab, and the dowels are modeled as a beam element. So the beam elements, and they are connected with the concrete slab of the brick element by the contact elements. So this has been modeled like this, and with this contact element, actually, it was possible to take care of the of the modulus of dowels support and the dowel looseness. So all those things were taken care of by these contact elements, and this was modeled here. And I have done a lot of parametric studies, and from that an expression was developed, and this expression for load transfer efficiency. So this load transfer efficiency, this expression was developed, and it was found that load transfer efficiency depends on all those parameters which was listed in the earlier slides. As you have seen here, that these are the parameters actually govern the load transfer efficiency. So here you can see that DL is the dowel looseness, S is the spacing of the dowel, L is the radius of relative stiffness, which takes care of the pavement, the modulus of subgrade reaction, and the elastic properties of the slab thickness. Beta is already defined here, and S is the spacing. So load transfer efficiency actually depends on all these parameters. That means the beta is also depends on this K value. You can see here that this is the modulus of the dowel support, the diameter, the elastic properties of the steel, and the moment of inertia, that is the area or the cross section. So it depends on the dowel parameters. It depends also on the radius of relative stiffness, which takes care of the pavement geometry and the subgrade strength. It depends on the dowel looseness. So all these parameters influence the load transfer efficiency of the dowel joint. So there are a lot of other things, but let us go to the load transfer at joints due to aggregate interlocking. So aggregate interlocking joints are provided when the traffic volume is relatively less, and the joint spacing is also relatively less, maybe a little less as compared to the high volume concrete roads. So for that, particularly when the traffic volume is less, in that case we can avoid the dowel bars and can provide and the load transfer can be done through aggregate interlocking. So this aggregate interlocking mechanism is here the load is transferred due to the interlocking action of the aggregate particles. So as I said, as I shown also in the earlier slides, that we cut the slab at 1/3 location or 1/3 depth, and below that cracks are formed. So those cracks actually help in transferring the loads that actually forms the aggregate interlock joint. And because of that, the load is transferred from one panel to another panel due to the interlocking action of the aggregates. So here, these cracks are joints with irregular faces. And in many cases, particularly in the longitudinal joints or so, we provide tie bars, not for transferring the load, but to ensure that the cracks remain tight and aggregate interlocking and load transfer can be done through aggregate interlocking. So tie bars, as I again saying, that tie bars are not for load transferring, but in many cases tie bars are provided so that it ensures the load transfer through aggregate interlocking system. So in aggregate interlocking, the interlocking action of the aggregates at the irregular joint faces, the load is transferred at the irregular joint faces, and due to the interlocking action of the aggregates present in the material in the slab. So if the joint face is very smooth, then there will not be any interlocking action, because in the construction joint, as you have seen, it is a full depth joint and it's smooth surface. So there will not be any load transfer unless we provide a dowel bar. But if there is an irregular face, a rough face, then there will be load transfer through aggregate interlocking. So here also similar way, tie bars are provided to help in interlocking action, not for load transfer, but for tying the two slabs in their position so that load transfer can take place through interlocking action. Now the parameters responsible for aggregate interlocking, load transferring, is there are many parameters. One is joint opening, size and angularity of the aggregates, strength of aggregate, because it is through aggregate only. So the aggregate properties are also important, are very, very important, particularly the size of aggregate. Okay, if it is very smooth aggregate, round aggregate, then it is, the load transfer will be less. So size and angularity of the aggregates matter. Length of aggregate, very soft aggregate will not provide good load transfer. And joint opening is the most critical parameter. If the joint opening becomes larger, then load transfer will drastically reduce. And distribution of aggregate within the cement paste, it is aggregate interlocking, so all the aggregate properties are responsible. Thickness of concrete slab also is important in case of aggregate interlocking. If the concrete slab is very thin, so then actually it will not get sufficient area also at the surface for load transfer. So thickness also important. Nature of fractured surface, as I said, the smooth interface or a smooth surface actually will not provide a good aggregate interlocking load transfer. So the roughness of the surface actually matters a lot for that. And of course, it also depends on the load and strength of subrail also. So these are the parameters, all the aggregate related parameters, the maximum size, the angularity, the strength of aggregates, and the joint opening, or the crack opening, or the crack width are very important for aggregate interlocking load transfer mechanism. And of course, roughness and other things, as I said. So it is the mechanism is the irregular faces of crack or joint in contact, interlocking action of aggregate particles help in transferring the load from one side, from one side to the other side. And load is transferred by the shear spring action. And this is also represented in the finite element representation. The aggregate interlocking also can be represented by a spring action, as if there are many springs are there at the edge. So it can be represented as a series of springs, like in modulus of subgrade reaction. So here also you can resemble it as a series of springs. So the spring stiffness actually depends on the nature of the cracked surface, that means how rough it is, and slab thickness, because you need the bearing area. And the nature of cracked surface depends on the maximum aggregate size, the crack width, the roughness, and the time of crack. So time of crack also is important, because if the crack is formed at very late stage, so then the crack width will be more, and there will be a lot of other implications. So the nature of cracked surface is also important for aggregate interlocking load transfer mechanism. So here is the finite element representation which I have done during my PhD work. So the series of springs actually represent the aggregate interlocking load transfer mechanism. So here also the load is transferred from the loaded slab to the unloaded slab. And these springs, spring action, this aggregate interlocking, actually it is the spring action due to which this load is transferred to the adjacent slab. And with modeling and with a lot of other analysis, actually what I have developed a new parameter, modulus of interlocking joint, to represent the strength of the fractured surface. So this parameter is termed as modulus of interlocking joint, and is a function of the crack width and the maximum aggregate size, which are the two most important parameters for aggregate interlocking load transfer mechanism I told earlier. So these are the two very important parameters, and the strength of the fractured surface depends on these two parameters, and based on that an expression or a parameter was introduced, modulus of interlocking joint, just similar to modulus of subgrade reaction. So this parameter is X is the crack width, and IR is the interlocking ratio, which I have introduced. This is aggregate size, maximum aggregate size by the crack. So this is the expression for that. And now this aggregate interlocking, actually, since there is no additional dowel bar or any other mechanism, so this also load transfer efficiency over a period of time may reduce. Even in dowel bar system also it may reduce due to dowel looseness and other factors. So here also aggregate interlocking load transfer mechanism, the efficiency may reduce over time. And what are the factors for that? Change in crack width, because initially the crack width is very small, so very good in load transfer. But over a period of time, the crack width may increase, so load transfer efficiency may reduce. Abrasion and attrition of aggregates, temperature variation. So all these factors may be responsible for reducing load transfer efficiency of the joint. So let us discuss about the effect of temperature on concrete pavement. Effect of temperature is okay. So this is all about for the moment all about dowel bar system and aggregate interlocking, but there are many more things, many studies have been done also by us, and but I will just give a very quick overview of the mechanism of dowel bar system and aggregate interlocking system, load transfer mechanism. And now I will go to the effect of interface actually in jointed plain concrete pavement, which is also a very important component, as I said earlier, particularly to take care of the temperature effect. So temperature effect is twofold in case of JPCP. One is the daily variation of temperature, another is the seasonal variation of temperature. In daily variation, what we have when we have the in daytime, particularly in daytime or night time, this daily variation of temperature effect is seen. So in daytime, the top temperature is more as compared to the bottom temperature. So there is a tendency of the slab to curl downward. That means the middle portion go up and the sides are at the lower level. While in case of night time, when the top temperature is less and as compared to the bottom temperature, so the slab is curled upwards. The sides go up, whereas this thing, the middle portion is at the bottom. So this is the curling effect. So if there is no restraint, this type of thing may happen. But in practice, do we see this type of thing? No, we do not see, because these curling effects are actually restrained. Okay, these are restrained due to many factors. One is the foundation, the adjacent slabs, the dowel bars. So all these things are actually the restraining factor, the self-weight of the slab. So all these things actually restrain this curling thing. So if it is free to move, so then there will be no stress. But because of all these restraints, the slabs cannot curl that much or curl up or down. So stresses are developed. So this stresses, we call it curling stress. And another effect is the seasonal variation of temperature. In seasonal variation, what happens in the summertime, due to increase in temperature, the slab tends to expand. And that is why these contraction joints or expansion joints are there to take care of these things. And while in winter time it tends to decrease. So there is a decrease in temperature, so there is a tendency of the slab to contract. So the joints are provided actually to take care of these thermal effects. So this is the seasonal variation of temperature effect on the concrete slab. And as I said, that interface actually plays a big role in taking up this temperature effect. So interface between slab and foundation is of two types. I think this slide also was shown earlier, but yes, I have put it here again. So one is bonded interface and unbonded interface. Slab is when slab is cast directly over the base, it is bonded interface, and the friction between the two layers is very high. And so in case of unbonded interface, there is a bond breaker, and the friction between the two layers is now reduced. So actually, this is the to take care of this temperature effect. Now, I will tell all this thing little later also. Now, this also we have done it, finite element modeling, the interface behavior, and the interface was modeled as with contact elements between the concrete slab and the base. So, and this contact elements actually, when there is a tension, there is loss of contact. That means it can take up that curling effect when there is a loss of contact. But when there is a high tension, that means the slab tends to curl up or down. So these contact elements will represent the loss of contact when there is a tension. Normally in compression, when there is compression, there is contact in between. But when there is a tension, so there is a loss of contact. So this takes care of the curling effect. So with this, it was modeled, the interface was modeled, and also what we have done, one experiment was done, one laboratory experiment was done, and to understand the friction characteristics between the slab and the base. As I said here, the bonded and unbonded interface. So this was how much is the friction developed between the layers. For that, actually, we have done the experiment. And sir has shown the one picture of that and he said that, okay, I will detail it more. So that I will do it. So there actually, we have done the push-off test. With that, with different types of base, that DLC and WMM, slab was cast, concrete slab was cast, and with that test, what we found that what could be the friction between the two layers. So here in this thing, you can see the first thing, this is horizontal displacement versus the coefficient of friction. So initial cycle, the friction was very high. But after that, we go on with repeated cycles, the friction actually reduces. So, so this second plot, you can see here that with number of cycles, the coefficient of friction, maximum coefficient of friction actually reduces significantly. And this friction value was used in the model, in the finite element model, to take care of the bonded and unbonded interface condition. So I'm not showing all those details. You can, if you are interested, you can go through my AC paper also on that. And so for that, with that, from that experiment, actually, we have obtained the coefficient of friction for bonded interface and unbonded interface condition, and for both for WMM as well as for DLC. And what we found that in DLC, the interface, the rough interface, it was so high that we could not move at all the slab. So the friction value was more than 20. So it was not possible to move because it was almost like a monolithic thing. So for rough interface, it was more than 20, but for WMM, we had some value in the initial cycle as well as for subsequent cycle. And for smooth interface also, we have obtained some value, as you can see from this table. So this is all from our experiment done here for bonded interface and unbonded interface. Now we have done some analysis also, and with different position of the load and with different temperature condition, that means seasonal variation, positive and negative, that means winter time, season, summer time, as well as daytime, night time, and with different load positions. We have done that finite element analysis, and with this bonded and unbonded interface condition, and the temperature was non-linear temperature variation was considered, and this thing you can see here that this is the temperature variation with distance actually with slab. This actually I have done some small experiment in the laboratory to find out the variation of temperature within slab. In the morning, sir has shown you that how the temperature varies in a slab in the field experiment, and this was done actually before that, and in laboratory we have done in a small scale and found out the variation of temperature. So there also we could get a very good variation, very good non-linear variation of temperature with positive as well as negative temperature variation, and this was used also in the analysis. And with that, we have found that we obtained the critical stresses at different locations on the pavement. You can see here from this picture also, this 1, 2, 3, 4, A, B, C, D, all are actually stress locations where we found out the stresses from the finite element analysis. And here we can see that for all load cases, only will load, only temperature, only positive temperature, only negative temperature, load at A plus positive, load at A negative. So all sorts of 17 combinations with uniform temperature increase, uniform temperature decrease, with slab, with wheel load, without wheel load. So many combinations we have done, and we found that the maximum critical stress was when the wheel load is at B plus positive, which one? Yes, for smooth interface, wheel load at A plus positive temperature gradient. Yes, wheel load at A plus positive temperature gradient. This has been taken also in the code also. It is there for other codes also, that when the load is at the edge and with positive temperature gradient, that is the critical condition, or the critical stress is developed at condition. So here also we have obtained for so many cases, and for rough and smooth interface condition, we found that stresses are developed, and stresses are less in case of rough interface condition when it is only wheel load cases, because in that case, actually, since the DLC is also contributing in taking up the load, so the stress development is also less at the bottom of the concrete slab. So in that way, the bonded interface is beneficial because the thickness requirement is less. But if you see here from this chart, if you see the stresses due to temperature effect, then for bonded interface it is actually more. So so in that case, to take up the temperature effect, the temperature stresses, the smooth interface is beneficial. So both have their benefits and limitations, but for our country, we have obtained, or we have selected for smooth interface for all our JPCP construction, because the temperature variation is significant here, both in summertime or in winter time, significant variation. So to take care of that effect, smooth interface has been taken up in the IRC. This is a few things about jointed plain concrete pavement. Another one, I will very quickly tell few slides, only 2-3 slides on white topping. And in recent years, jointed plain concrete pavement is constructed in many places, particularly in highways. It is very good option. But in urban roads where the traffic volume is not so high, or semi-urban area, or in other places, white topping is also another type of pavement which is coming up also. And this is also good for relatively less traffic volume roads. So it is white topping is a concrete overlay over a distressed bituminous pavement. It is actually a rehabilitation measure of an existing bituminous pavement. It is the concrete overlay. So the below layer is the bituminous, has to be a bituminous layer, and that is why it is called a white topping. Over a black top, it is the white topping. Its concrete is more or less whitish in color. So white topping is another thing, and I think more details will be discussed also in this course by Dr. Ramachandra. But I'll just few words I will just share. So in white topping, compared to JPCP, we have lesser spacing of joints, 1 meter to 1.5 meter in either direction. It could be square or it could be rectangular. Thickness is also less. Normally in JPCP, we have 250 mm onwards thickness, maybe 250 to 350 or 400 mm also is possible, depending on the traffic. And but in case of white topping, the thickness is much less, 100 to 200 mm. And for that, we have to have a minimum thickness of bituminous layer, because here the existing bituminous layer acts as the base layer. Instead of the DLC, it is the bituminous layer that acts as the base. So minimum 75 millimeter or so, or 100 mm bituminous surfacing is necessary for the construction of white topping. And subgrade value, this is from the code only. I have taken subgrade value here. It is recommended that more than 15 kg per centimeter square per centimeter. And the same concrete grade, it is M40 grade of concrete as used in JPCP. Here also in white topping we use for M40 grade of concrete. And concrete is, in JPCP, concrete is normally plain concrete. But here it is plain concrete also is possible, but it may also be fiber reinforced. Very fine fibers may be used, or high strength concrete also may be used. Self-compacting concrete can also be used, and these things are new things also coming up. So fibers could be steel fiber, could be polypropylene fiber, very thin and long fiber, or it's actually microfibers can be used in very small quantity, 0.3 to 0.2 to 0.3%, not more than that. And here the interface should be bonded or unbonded or partially bonded, but it should be to ensure that the existing bituminous surface is a rough surface, so that there is a proper bonding, because the thickness is less as compared to JPCP. So that is why it is preferred to have a bonded interface. And panels are packed by saw cutting up to the 1/3 depth as in JPCP, but here the joint width is also less. And one important thing is that it doesn't have any double bar. So all load transferring is due to the interlocking action of the aggregates. So we have done some small analysis, and now the work is going on actually. So this is just a 2-panel pavement and aggregate interlock joint, and the finite element analysis was done. And so this is the pavement, 1.75 by 2 meter pavement. Actually, this was this pavement has already been constructed in Nagpur, and that analysis was done by us. And we have done the finite element analysis and checked the stresses at different locations. You can see here that A, B, C, D are different locations of the pavement and of the wheel load on the pavement. And we found out the stresses, and based on that, the design was suggested. And we have checked also the stresses with different joint spacing, and found that when we increase the joint spacing, the flexural stress actually reduces. And this flexural stress, we have also compared it with JPCP stresses, and it was quite less. And actually, because of this smaller panel sizes, the temperature stress is much less. So the total combined stress is also less. So that is why the white topping is also becoming popular nowadays, because the joint spacing is less, no dowel bar is required. And if you go on here, you can see that if you go on increasing the joint spacing, the stresses also increase. So that is done. So this was a small work done for that Nagpur road. And so this is coming for particularly for moderate to low traffic area, and it is very good option for urban roads. In urban roads, we do not have so many commercial vehicles, but it is very good option for, and they provide a very good service life and smooth riding to the urban areas. But more work is now going on, and so we will tell more when we will do those things. So that's all for today. I am closing here, and I will be happy to answer some of the questions if you have. Thank you.
Thank you, madam. Thank you for your elaborate presentation, madam, on various aspects related to rigid pavement. And I'll just go through the chat box, madam. You also can go through this one when some of the questions are there.
Yes. Yes. The questions are there in the chat box?
Yes, madam.
Okay, or we can interact also.
Otherwise, just I'll read the questions, madam. You can answer, no problem.
Okay. Okay, I'm just telling few words in white topping. But the first question is on white topping. I think you will have another presentation by Dr. Ramachandran, no?
Yes,
By,
ma'am.
on white topping. Okay, but anyway, I can tell you. In white topping, actually, it is actually the concrete overlay over an existing bituminous pavement, and since the mm, the joint spacing is less, so we have found that the stress developed is also less here in case of white topping. And as I said, that it is for moderate traffic volume roads. In JPCP, when I was discussing the JPCP, I said that double bars are essential, and it is the only option when we have high traffic volume roads. And in case of white topping, it is not for highways. First, I would like to say that it is not for highways, and so it is for moderate traffic, and the road the thickness also is less. That is why the thickness also is less. The stress developed is less, so we can avoid dowel bar here. And but in case of white topping, also if you have a construction joint, you have to provide a dowel bar, both in transverse as well as in longitudinal direction.
Madam, so what is the generally the level bar generally we provide at the joints, construction joints in white topping, diameter of the level bar?
Diameter of the dowel bar you can take like in JPCP. Similar to that, say for 200 mm thick or 250 mm thick, what is the code has been given. So you can use that dowel bar.
There's another question, madam, about that one. What are the main parameters that affect bonding of concrete slab with foundation? Also, madam, in your opinion, which software is suitable for FD modeling of concrete pavement and its interface?
Just one second, please.
Madam, what are the main parameters that affect bonding of concrete slab with foundation, madam?
Okay, what are the main parameters? No, if you construct a pavement directly over a DLC or so, then it will create a bonded interface. Okay, so it is the roughness of the two layers that matters. It is the roughness of the two layers that matters how much bonding is there in between the two layers. So if there is no other material, then since the roughness of the two layers are more, so you will have a very good bonding. And if the roughness is reduced by placing a polythene sheet, so in that case, you will have a smooth interface.
Madam, next the question is, in your opinion, which software is suitable for finite element modeling of concrete pavement and its interface?
Okay, there are many softwares available. All commercial structural analysis software can be used for finite element method. You can use Abacus, you can use ANSYS, you can use NISA, you can use others, Athena, or there are some specific concrete pavement analysis softwares also available, like Kane Slab, like Ely Slab, but you have to purchase those things.
Is there any questions from the participants?
In the chat box, it is there. Do we have to consider the effects of earthquake while designing a concrete pavement if the pavement is to be constructed in earthquake-prone areas? If yes, then what changes do we need to adapt while designing? So far, not considered. So far, the earthquake effect has not been considered. This has not been considered so far in the design.
I think already Madam explained this question, but again there are why double bars can be avoided when the joint spacing is less.
See, this I have explained that even for not only for white topping, but for normal concrete pavement, for jointed plain concrete pavement also you can avoid double bar. Since the traffic volume is less, you can go for aggregate interlocking joint with lesser spacing, with lesser thickness, because the final load coming on the pavement is less. So in that case, you can avoid double bar for any pavement. It may not be white topping, but for any JPCP, if the traffic volume is less, you can avoid double bar.
Madam, the last question, madam. Can we design concrete road with bonded consideration in brackets? Can we design concrete pavement with bonded consideration? Is it advisable?
Yes, we can design, but directly you can cannot use whatever has been given in IRC 58. IRC 58 has been developed considering unbonded interface, and so it is the one concrete slab and the foundation as a whole has been considered. So it is the unbonded case, but you can do it considering, remember that you have to consider the stresses which are developed due to the bonded interface case. So for that you have to analyze it and take those stresses and do the fatigue analysis and stress calculations. So you can do it.
Okay, madam. Thank you, madam.
Okay.
Thank you, madam. First of all, let me congratulate madam from our institute. We have done a lot of work in the concrete, especially load carrying mechanism at the joints, madam. So please allow me to provide the conclusion remarks.
Okay, then.
Dr. Swati Maitra started the presentation by explaining various types and characteristics of rigid pavement. Madam has discussed in detail on joints in rigid pavements and arrangement of double and tie bars of joint locations. She explained elaborately on load transfer mechanism of double joints and aggregate interlocking joints and possible failures due to poor load transfer. Analysis of joints and load transfer mechanism by finite element analysis was very well discussed. Madam also explained the interface behavior of concrete slab with respect to the base layer and how to model the same using the finite element analysis. So, Madam also explained variation of stresses in bonded and unbonded concrete pavements, considering the different type of loading and temperature combinations. At the end, Dr. Maitra explained the white topping, explain about the white topping and its characteristics. Madam, we from the Department of Civil Engineering and the Institute, we thank you for accepting, once again, we thank you for accepting our invitation, madam.